Part A. On each dot, draw and label the forces, not components, exerted on the blocks. Each force must be represented by distinct arrows starting on and pointing away from the appropriate dot. So, yeah, that's a very ugly incline, but whatever. So normal force is going to be perpendicular to the incline. You have mg going straight down, force of gravity, and then you have the tension parallel to the incline. For block B, it's just hanging, so F of G down and tension up. Yeah, I was an idiot, man. I drew out the components for force of gravity. Part B, derive an expression for the magnitude of acceleration of a block after the blocks are released. Express your answer in terms of m, theta, and physical constants as appropriate. Okay, so we're just gonna find the acceleration of the total system. So here the tension is equal to gravity. Here the tension is equal to gravity sine theta. So you have this is the force of gravity on block A. This is the force of gravity on block B. So you have 5 ma equals to 4 mg sine theta plus mg. And you just simplify from there. So A is equal to 4g sine theta plus g over 5. That looks a little bit hard to read, so I'll just write it bigger. A is equal to 4g sine theta plus g over 5. Yeah, I did nothing wrong on this part. Part C, on the axis in figure 3, sketch a graph for the magnitude of the net force as a function of the inclined angle for each following subjects, block A and block B. So I think I have enough room. Yeah, I'm not gonna make this to scale. So block A will, at 98 degrees, it'll be in free fall because it'll just be like a straight line down and there's no friction of the wall per se, so it's just in free fall, which means it'll be 4 mg at 90 degrees. So block A will end way up here. Block B, same thing, it's just gonna be in free fall, so it's just mg at 90 degrees. since it's sine data for the gravity component, it's going to be curved. And since that the how do I say this? The acceleration at 0 theta for block A will be 4/5 mg, and block B will be 1/5 mg. So neither of them start at 0. So about here-ish, that's not drawn to scale. Do not even think that is drawn to scale. What I did wrong was that for both of them, I set the initial force equal to 0, so they both started down here for mine. And then I forgot to include the sine theta, so instead of making them concave, mine were just straight lines to the endpoints. For part D, describe how the graph for block A and part C would change if the string and block B were removed and block A released from rest on the incline. So, I forgot what I wrote, but I know that even if block B is removed, when it's at 90 degrees, it'll still be in free fall, and the net force will be just gravity. So at 90 degrees, it will still have a net force of 4 mg. To go along with that, without the string, when it's at 0 degrees, that means like it's completely horizontal. That means that the horizontal forces, there are none because there's no tension, and then the vertical forces, gravity and normal force, just cancel each other out. So net force is 0, it just remains at rest. So that means it has like a initial net force of 0. What I did wrong is that I didn't specifically state either of these facts. I really just said that according to the acceleration thing or whatever, the formula from part B, that 4g sine theta would increase. I assumed that this would have like a smaller slope, and that, yeah, I just made up some crap.